In this example, we'll walk through step by step the creation of an external cover for this plant pot. The plant pot will be created using 3D printing, and the colour of the filament used to print the part will be chosen to reflect the colour of the flowers of the plant. The design will allow the existing plant pot to be placed inside. Therefore, the first step is to measure that existing plant pot. The measured dimensions will be used to create a CAD file, which will be converted into a 3D printable G-code file. The key dimensions for the plant pot were measured at 100 mm at its narrowest point, 130 mm at its widest point, and 95 mm tall. The shape of the plant pot will be based on hexagons, some of which will be rotated around their axis to create a curved or swept design. The software chosen to model this part is Rhino 3D. Rhino is a surface modeling software which lends itself to the curved design that is intended for this part. Created first are circles that represent the measured geometry for the existing plant pot. These are converted into surfaces that represent that existing plant pot and gives us a reference to build our design around as we move forward. Next, another set of circles are created. These will act as a guide to help us locate the hexagons, which will later create the outer surface of the plant pot. Next, the hexagons themselves are created, with the center hexagon having a 30-degree rotation relative to the first, which will allow a sweep to be created. When the surfaces are created, they will sweep along this line, creating this spiral pattern. The surfaces are created using a sweep, following the line of the points outlined earlier. We can see that the original plant pot fits inside this geometry. But to allow a little bit of space around the plant pot, we create some offset surfaces, which will be used to create the hole in the middle of our new design. These surfaces will be joined with the swept geometry created previously to create the basis for the plant pot design. Here we use what's called a Boolean operation to remove the volume, the shape of the hole from the swept design. To soften the shape, fillets are added along all of these edges and along the top and bottom edges of the design. For drainage, a small hole is created at the base of the pot using a small cylinder, and again removing the material using a Boolean. Other features like chamfers can also be added at this point. The final geometry is now exported as an STL file, which can then be processed in specialist 3D printing software ready for printing. The STL is imported into the software and aligned to the base of the 3D printer. The orientation is chosen to help make the printing process easier and less wasteful. If the parts were orientated differently, it may result in a large amount of material having to be used to support the print, as the FFF process chosen for this project requires geometry beyond 45 degrees to be supported by support material, as we can see in the first and second example. Orientations like these would cost more money as they require more material and more time, both to print and to clean up. The other effect of print orientation is layer lines, and layer lines can affect both the strength and the aesthetics of the part. The orientation on the right was chosen as it requires the least support material and would orientate the layer lines in the most aesthetically pleasing way for this design. Strength is not as much of a concern for this part as it is not heavily loaded. Now that the part is orientated on the build plate, the next step is to choose the print settings. This printer is using a 0.8mm nozzle and will have a layer height of 0.7mm, and 3 perimeters will be created around the outside of the part to create the wall thickness. The next setting is whether or not we have a solid or hollow part. In this case, 15% infill will be chosen, meaning that 15% of the inside of the part will be filled with some kind of structure, which in this case will be a gyroidal structure which is based on a curve. While there are many other settings that could be chosen, with these basic settings it is possible to now export the combined G-code files for the printer. But before doing that, we can take a look at the preview, which shows the 3 external walls and the 15% gyroidal infill taking up some of the inside of the part. Here we can see the curves that drive that gyroidal infill. Once the part has been examined, a G-code file is created and exported for use on the printer. The chosen material is inserted into the printer. In this project, that's a copper-coloured PLA material with a print temperature of 210 degrees. This is pushed through until it is extruding cleanly. The SD card containing the G-code file is inserted into the machine and the relevant file is selected on the screen. After preheating to the required temperature, the printer begins the printing process, laying down the first layer on the print bed. The filament is pushed through the heated nozzle and extruded in a thin bead onto the print bed, building up the first layer of the print. The printer displays the time remaining in the print as well as the material temperatures for both the nozzle and the bed. The printer continues to build up one layer on top of another until the part is completed. The 0.8mm nozzle leaves a distinct pattern on the surface of the part due to its coarse nature. This can be part of the appeal of a 3D printed part. As the part is completed, the top surfaces are filled in with a solid infill to close off the top surface. The part can be removed from the build plate and finished as required with sandpaper, fillers and spray paints. Or it can go directly into use, as with this design.